Good day, students. Myself, Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dungar College, Bikaner. I welcome you all in the lecture series of MSc Previous Physics. I am dealing with the first paper, that is Classical Mechanics, and we were discussing central force problem. That means we are solving our problem in r theta polar coordinates. Now, in our today's lecture, we are going to derive the shape of orbits. And as we know, the total energy, it will be the sum of kinetic and potential energy. And the kinetic energy is half m r dot square. And the potential energy, it arises from the two terms. One is the factor which comes from the contribution from central force and another comes from the contribution from centrifugal force. This term corresponds to the term related to the centrifugal force, and the potential energy related to the central force is expressed as VR. So, I have my total energy as half m r dot square plus L square upon 2m r dot square plus VR. I am taking my central force as k upon minus k upon r square. So, my potential energy, the central potential energy will be minus k by r. And in accordance with this, the total energy E will come out to be half m r dot square plus L square upon 2m r dot square minus k by r. Here k is constant. Now, as we know that total energy of the system is always constant. This is the condition for conservative cases. Now, as we know that central force problem, it is a problem of conservative system. Hence, in this case, E will be constant. So, at the turning point, the value of R, let it be minimum. And we are well familiar with the fact that the turning points corresponds to the situation in which the total energy will be minimum. The total energy at R equal to R minimum, it will be have a value which can be expressed in a form. Here I am using R to be minimum. If R is minimum, then its derivative will be equal to 0. So R dot will be equal to 0. Hence first term is 0, and in the second term I have L square upon 2m r square, which is L square upon 2m r minimum square minus k upon r minimum. So using this energy, I am going to find the value of the factor eccentricity, which appears in R. This is the expression of Kepler's first law, according to which the shape of orbitals is conical, and the factor epsilon, termed as eccentricity, decides the shape of orbital. That means whether our conic section will be parabola, hyperbola, or whether it will be elliptical. So, using the condition of R minimum, I have R minimum as P upon 1 plus epsilon. Here P is L square upon mk. Now, using the value of R minimum from this expression, in energy I will have E as L square upon 2m, substituting R minimum, which is P upon 1 plus epsilon. minus k upon r minimum is p upon 1 plus epsilon. Solving this expression, I will get my total energy as, in a simplified form, as mk square upon 2l square epsilon square minus 1. Now, from the value of energy, this is the value of energy. Here, the factors which are constant are L, M and K. But eccentricity epsilon is not known to us. This epsilon is the deciding factor for the shape of orbits. Now, from this expression, I have obtained my eccentricity. Epsilon is 1 plus 2e L square upon mk square raised to the power half. Using this and taking the value of p as L square upon mk, I can obtain the value of r. R is p upon 1 plus epsilon cos theta. Substituting the value of p, L square upon mk, 1 plus eccentricity as 1 plus 2e L square upon mk square. This whole raised to the power half multiplied by cos theta. This gives me the value of my r, which decides the shape of my conic section. Now, in this expression, I am taking the different conditions of total energy. Let my total energy to be positive. That means it is greater than 0. In the situation in which epsilon is greater than 0, this will give my eccentricity as greater than 1. This situation is that of hyperbola. Epsilon greater than 1. As we have discussed in our previous lectures that epsilon greater than 1, the situation corresponds to that of an hyperbola. Now, I am taking a situation in which the total energy E is 0. Then in this condition, epsilon will be 1. And epsilon equal to 1, this gives me the shape of a conic section which is parabolic. In the third case, I have a situation in which the total energy will be less than 0. That means from the equation we can see that total energy less than 0 corresponds to a situation in which epsilon is less than 1. That means the shape of orbital will be elliptical. So, epsilon eccentricity is the deciding factor to determine the shape of our orbital, whether it will be hyperbola, parabola or elliptical. And our Earth is a planet which revolves around the Sun in the case of elliptical orbits. That means the situation in which epsilon is less than 1, and this is the case of elliptical, that means its motion is periodic motion. And the other two situations, which are the case of hyperbola and parabola, they are the situations of non-periodic motion. So, we are considering the situation where epsilon is less than 1. That means total energy is less than 0. Motion is periodic. And in this periodic motion, the shape is elliptical. So we have semi-major axis and semi-minor axis of ellipse. I am going to derive the relation between the energy and semi-major axis of ellipse. Semi-major axis is A, and we have derived the expression of semi-major axis of ellipse in our previous lectures as A is P upon 1 minus epsilon square. Here P is L square upon mk divided by 1 minus epsilon square. On solving this, I get 1 minus epsilon square as L square upon mka, and we have derived our energy as mk square upon 2L square epsilon square minus 1. So using my energy, using this formula of energy and substituting the value of 1 minus epsilon square, I am going to derive the relation between E, energy, and semi-major axis A. Substituting the value of epsilon square minus 1 and solving, I get my energy as minus K upon 2A. So this is the relation between energy and semi-major axis of our elliptical orbits. We can say for those orbits for which semi-major axis A is same, that all orbits will have the same value of energy, because energy depends only on the factor A, as K is a constant. It depends only on A. If A is same, then total energy of orbital motion will be same. So E can be expressed as minus K upon 2A. So in our today's lecture, we have derived the shape of our our orbits, which depends on eccentricity. Thank you students for watching.